So this work is about a tool we've built, and Dury Long was supposed to give this talk as well as present a short paper that was based on this tool. Unexpectedly, she couldn't make it, so I get to present both papers. So the problem we are working on is difficulty detection. We assume that the user is a programmer interacting with the programming environment and maybe a browser. And we'd like to determine if the programmer is facing difficulty at a certain point in time. Okay? The way we do it is by logging users' interaction with the interactive tools, extracting features from these actions, and running using these features as input to a difficulty detection algorithm that tells us whether the answer is yes or no for the difficulty. So any machine learning algorithm would not be perfectly correct, so it would have some false positives and some false negatives. And if we want to improve the algorithm, we'd like to know why things went wrong. And to improve an algorithm, we also need to understand what's happening. Machine learning algorithms are complex algorithms, typically not written by us, but some common algorithms such as decision tree, which is what we used here. And we'd like to know why things went right so that we better understand what happened and which features are important and which are not. So the terms why and why not were introduced in a lexicon by Andrew Coe and Brad Myers. And the general problem is that given some input, when we don't see the correct output, we'd like to know why it didn't appear. And when we see some incorrect output, we'd like to know the cause for it. And if you're trying to understand program that we wrote a long time ago or that we did not write, we'd like to also know why the output is correct at a detailed level. Okay? So there are many ways to, there are many tools to try to answer these questions in general and in more special cases. A debugger, a classical debugger, provides the most general approach in which you can single step through a program and see the relationship between input and output variables. Instead is an idea that builds on the notion of a classical debugger. This is an idea in many tools built by Phil Guo for different languages, and this is JavaTutor. And JavaTutor is much like a debugger. You can step through the program and see the values of the various variables and see where you are in the program. Unlike a conventional debugger, you don't step through the program while the program is executing. The system executes the complete program, stores the information in a history, and then gives you a timeline that lets you step back and forward in the history to understand what happened, why things went wrong and why things went right. So here it tells us that we are on line 4 in the main program, and the value of j is 0, and we are step 3 of the execution, and there were 14 steps that were executed. And I can go forward, and now it tells me that I'm at the same line, but executing a different iteration of the loop, and now the value of j is 1. I can go back, see that the value was 0 in the previous iteration. So we can try to apply this general tool to our problem. We can use we can run our algorithm first online, make predictions, and then we can run it offline using the timeline that JavaTutor has, and look at various points in the program and see why it behaved the way it did, going forward and backwards in the execution. So that approach could work, except that we would be using an algorithm that we haven't written. Like I said, we use decision tree. And we're not interested in the intermediate variable values. We're interested only in the external variables, the external input variables and the external output variables. And in our case, the input variables are the features and ground truth, and the output variables are the predictions. Also, we're not interested in every step that the program takes. We're only interested in steps when predictions were made, and predictions are made every n commands, we go and divide the log into fixed length segments, and each time a new segment is input, is completed, in fact, we make a prediction. Okay, so that's how the system doesn't quite work, but the basic idea can be applied if you can just provide a coarser-grained view of what is happening. That a view that only the external user would be interested in. And what we've done, we also have a timeline with an x-axis and a y-axis. And in JavaTutor, each code step corresponds to a value on the x-axis, and the y-axis shows all the variables and their values. In our case, the x-axis corresponds to segment number when a new segment was input by the user, and the y-axis shows you the input features, the input ground truth, and output actual predictions. Okay? So that's the basic idea, and what our poster will show are the tool details, the UI, which is beyond the scope of this talk, and also will tell us, will explain the answers to some why and why not questions that were based on a study we did using the tool. Okay, so that's and I've taken more than my allotted time, so let me end at this point.